Welcome, future psychologists. Let's jump right into this session. Today, we're putting major depressive disorder, or MDD, under the microscope. We're going to look closely at the complex diagnosis and the fascinating biology underneath it. Think of this as a diagnostic funnel. We're going to start super wide with global data, move through the messy challenges of diagnosis, and then zero right in on the neurobiology. Ready to expand your clinical perspective? Let's get into it.
So, according to the World Health Organization, about 4% of the global population is experiencing depression at any given moment. Now, 4% might sound like a tiny fraction, but we are talking about hundreds of millions of people here. It's literally one of the leading causes of disability worldwide. It drastically impacts daily functioning, hitting a patient's ability to work, maintain relationships, and regulate emotions. This really grounds us in the massive global scale of the problem you'll be facing in your future practices.
And here's the tricky part. Diagnosing depression isn't just about ticking boxes on a simple checklist. MDD is notoriously difficult to pin down because it is a highly heterogeneous condition. It presents this really broad spectrum of either-or symptoms. One patient might have chronic insomnia, while another is sleeping 14 hours a day. One might lose a ton of weight, another might gain it. These polar opposites can be incredibly confusing for both the patients experiencing them and for us clinicians trying to make an accurate diagnosis.
Okay, so here is our game plan for today. We'll cover the diagnosis of major depressive disorder, the challenges with diagnostic validity, the diathesis stress model, the cortisol hypothesis, and finally, how cortisol physically changes the brain.
Section 1. The diagnosis of major depressive disorder. Let's dive into the macro-level demographic data. When we look at the statistics, women are consistently reported to experience depression about 1.5 times more frequently than men. That's roughly 6% of women compared to 4% of the male population. And this gap shows up all over the world. Naturally, it makes you wonder, right? Is this strictly biology, environmental factors, or maybe it's the way our healthcare system is fundamentally designed to diagnose?
What's really interesting about this slide is the incredible visual dichotomy of how these symptoms present themselves. Diagnoses can have massive blind spots. Women generally report symptoms like sleeping too much, comfort eating, anxiety, and longer depressive episodes. But men? For them, depression often masks itself as substance abuse, extreme irritability, or really risk-taking behavior. What this means is that male depression might be systematically underreported or misdiagnosed simply because those symptoms don't perfectly fit the classic clinical picture we look for in standard questionnaires.
Moving right along to Section 2, the challenges of diagnostic validity.
Let's talk about socioeconomic status because it plays a gigantic role here. People from lower socioeconomic backgrounds face chronic stressors like financial instability, and they objectively have fewer protective factors like good healthcare access. Johnston's 1989 research gives us some vital empirical data on this. It shows that due to systemic disparities, lower SES patients often receive more severe diagnoses right off the bat and are pushed toward biomedical treatments rather than psychological therapy. It's a structural reality in the healthcare system that you absolutely need to keep in mind.
We are also seeing a global rise in the prevalence of these diagnoses. Kessler, back in 2005, suggested 3 main reasons for this. Maybe we're just getting better at spotting undiagnosed disorders. Or maybe there's a genuine increase in mental health struggles due to modern life. But the third reason is super thought-provoking. Ask yourselves, are we pathologizing previously normal behavior? This is a crucial question for you to critically evaluate the cultural validity of manuals like the DSM and ICD.
Just look at this quote. It really hits the nail on the head. In the past, someone who actively avoided social contact was just considered, shy. Today, that exact same behavior, depending on its severity, could be labeled as avoidant personality disorder. Our diagnostic manuals might have actually narrowed the definition of what's normal. So in your practice, it's always better to understand behavior on a fluid continuum from normal to abnormal, rather than forcing people into rigid either-or boxes.
Which brings us to part 3, the diathesis stress model and depression. Let's shift from the what of diagnosis to the why.
Mental disorders rarely have just one simple cause. Instead, they develop through this complex interaction between underlying vulnerabilities, that's the diathesis, and active stressors. Vulnerabilities can be biological, like the 5-HTT gene, cognitive, like Beck's negative schemas, or sociocultural, like early childhood trauma. On the other side, you have the stressors, which are triggers like a sudden loss or major life events. Basically, you might have the vulnerability, but it usually takes a significant stressor to pull the trigger and activate the disorder.
Caspi's breakthrough 2003 study illustrates this interaction perfectly.
His team looked at individuals with a short version of the 5-HTT serotonin transporter gene, and they found that these folks were indeed more likely to develop depression, but, and this is a massive but, only if they also experience stressful life events. The key takeaway here, biology alone doesn't cause depression. It just drastically increases your nervous system's sensitivity to stress.
Of course, vulnerability isn't just in your DNA. It's also in the architecture of your thoughts. We have cognitive vulnerabilities like Aaron Beck's famous cognitive triad, negative schemas about yourself, the world, and the future. Then there's Albert Ellis's ABC model exposing our own irrational beliefs. And we absolutely can't forget Susan Nolan-Huxema's response styles theory, which highlights how rumination, endlessly chewing on negative thoughts, actually maintains a depressive state. Guiding a patient toward healthy distraction instead of rumination is a vital defense mechanism.
All right, Section 4, the cortisol hypothesis and the HPA axis. Let's get into the physical neurobiology, because this is where things get incredibly intense.
So what exactly is the cortisol hypothesis? It suggests that the diagnosis of depression is intimately linked to long-term elevated levels of cortisol, our primary stress hormone. When the HPA axis becomes overactive, it floods the body with cortisol even when things are supposedly calm. This relentless chemical flood keeps the brain in a constant state of stress, completely disrupting mood regulation and messing with crucial neurotransmitters like serotonin and dopamine.
Let's map out this biological sequence and see how it builds. Normally, stress triggers the alarm in the HPA axis. Cortisol is released. That cortisol travels to the brain and binds to glucocorticoid receptors in the hippocampus. The hippocampus then says, okay, message received, we're safe, and signals the hypothalamus to shut the alarm off. It's a brilliant negative feedback loop, but the problem is chronic stress completely breaks this loop down.
And that brings us to our final section, how cortisol changes the brain.
To really visualize what chronic cortisol exposure does to the brain's architecture, let's use a metaphor. The hippocampus acts as the brain's brake system for stress. It's literally the mechanism that stops the galloping fight-or-flight response and helps your tired body return to chemical balance once the worst is over.
But what happens if you drive with the brakes on for weeks, months, or years? The brake pads wear out and get destroyed. That's exactly what happens in our heads. Videbek found in 2004 that individuals with depression literally have a smaller hippocampus. It just shrinks. And Vershek-Schallhorn in 2013 linked an abnormally high cortisol spike upon awakening to a huge risk of recurring depression. Chronic exposure to cortisol physically destroys and weakens hippocampus cells.
This hits right at the heart of neurogenesis, the incredible natural process of growing new brain cells. Toxic, high levels of cortisol severely choke off this regeneration. And this perfectly explains why individuals in a heavy depressive episode struggle so much with memory and learning. We now understand that depression isn't just a simple chemical imbalance, it's a physical reduction in the brain's fundamental ability to adapt and repair itself.
But the neurobiology doesn't leave us without hope, and this is an empowering message you have to share with your patients. Simple, regular physical activity forces the body to burn off that excess cortisol while rewarding it with a boost of endorphins, dopamine, and serotonin. It helps reset that broken HPA axis. And this is why clinical treatments often take a few weeks to work. They aren't just stabilizing chemistry in the moment. They are actually supporting the safe, gradual process of neurogenesis, giving the brain time to regrow those lost pathways.
As we wrap up today's explainer, I want to leave you, our future clinicians, with a final, provocative thought. Knowing that modern treatments are fundamentally targeting neurogenesis and rescuing the brain from cortisol, rather than just tweaking chemical imbalances, how will this hard biological reality shape your future approach to diagnosis and clinical interviews? It's like a giant puzzle, right? Think about how multidimensional your role is going to be. Thank you so much for your focus today, and I'll see you in our next session.